Okay, welcome everyone. This is special topic in scalable data science. It's quite packed. There's still a couple seats left, so that's good. So I'm Raz. I'm the course coordinator, and there is Siva. He's actually one of the co-instructors. So it's a sort of an industry academia effort. This course is actually sponsored by Databricks Academic Partners Program. So University of Canterbury is a permanent Databricks academic partner. And it's also supported by the Amazon Web Services Educate grant. University of Canterbury, again, has in fact, a couple thousand faculty every year from UC already have access to about $200 US, and every student as well. There's some upper bounds on it, but there's a lot of cloud computing credits. So the course is run through those infrastructure grants. So this is the time and place for interaction. So basically the course URL is www.math.canterbury.ac.nz/r.sinudin, SAINUDIN/courses/scalable data science. So you can easily find that by just Googling me. You'll come here, which is just me. This is when I was handsome a while back. And here is courses under teach. Oh yes, that's a good point. So you'll get to log in 1 minute. So Paul is sorting out some issues there. So there we go. Thank you. So let me start again. So if you Google me, you just come here and courses and 2016. This is basically where all the information is going to be communicated from. So the time and place for presence is 4:30 p.m. to 6 p.m. This is kind of an industry timing, so officially we're supposed to run from 4:30 to 6:30 for honors courses. So people don't have to stay after 6 p.m. But that's when we're going to probably get into the more homework bits, which will be more interesting. So the interaction in cyberspace is mostly streaming with minimal interaction. There are a couple people from Wellington and one from New York City. And hopefully they can join in. In terms of course material, everything will be done through this particular URL. I'll get you guys to log into that in about 20 minutes because we're getting some new people's accounts set up as we proceed. So let me just jump straight to the content. This is prepared by myself and Siva, as I said. A bit about who your instructors are. So I'm from academia. I've about 10 years of experience in academia, including my 3 postdoc years actually. And just last year I had some industry experience, so I'm really mostly academic. There's some LinkedIn IDs here and my CV. I'm kind of interested in lots of things. I just work with people rather than any particular area of mathematics. So I just have publications just in different fields, depending on who I sort of play with. So this includes computational, computable mathematics, computational statistics, mathematical and statistical population genetics, statistical physics, various applications in biology, so it's very data dredging stuff, air traffic computing, gas turbine identification and control with mechatronics at UC, applications of natural language processing, terrorism studies, sort of a pet peeve, and then some art and education. Okay, so that's just very briefly about me. And Siva comes from industry. He's got 11 years of experience. So this is Siva's LinkedIn. He's sort of really fielding the hot pipes under the hood here, right? So he's what I guess is a data engineer. And so he has a lot of experience at various companies, mostly in India. He just moved to New Zealand. And you can, I guess, read about it, but he comes at things from a technical architect's perspective. Okay, so what is scalable data science in one picture? This is basically stolen from Wikipedia, so this is heavily hyperlinked for you to play around and dig deep. But scalable data science is basically big data science. I don't want to use the word big because basically you don't have to say bigger and biggest and biggest and so on. So it's basically scalable. So and we'll study what scalable really means shortly. The basic core idea is that you have domain expertise, core skills in mathematics, statistics, and computer science, and some kind of entrepreneurship angle that's driving the whole process, right? So basically raw data gets collected, data is processed, data is cleaned, models and algorithms are built using usually maths and stats skills. So all these arrows are actually pointing to different boxes in the process. So once you clean the data, you have to do exploratory data analysis and use those insights to do models. Then you have to go back to the process itself and do what's called feature engineering and refine the models and communicate the results. Hopefully build a data product using some entrepreneurial angle so you can serve that back to the world where the data is really collected from. Because I guess we all want to make a living, right? So that's basically scalable data science. You're more than welcome to read these ACM communication links. So if you're enrolled for the course formally, you'll be able to go through the UC library. And here are the key insights from this really interesting article. The data science is the study of the generalizable extraction of knowledge from data. So this is Russ and Dar in Data Science and Prediction. A data scientist requires an integrated skill set spanning mathematics, machine learning, artificial intelligence, statistics, databases, optimization, along with a deep understanding of the craft of the problem formulation to engineer effective solutions. So, remember, we need to make money, right? To make a living or whatever. So it's the full process. So the key insights in this really, another elegant paper in Science last year, this actually focuses on the Berkeley data analytics stack that we're building on. Tell you more about it. This is a nice paper by Michael Jordan. And here the key insights are that, for a lot of current problems, so if you just go right-click this and just to jump right into the science paper, because this is open access, I think, so it should just load up. And you will start seeing that lots and lots of problems across multiple domains are actually falling in this. We'll wait for it to load. Okay, so what are the key insights? Adoption of data science and machine learning methods is leading to more evidence-based decision-making across health sciences, manufacturing, robotics, autonomous vehicles, vision, and so on, right? Marketing and administration. Okay. How are we developing all this content? So this content is actually in GitHub, and it has hooks to Gitbook, and it's completely unlicensed from our end, me and Siva's end. But it's building on top of various other licenses, right? So the main sources of information are actually the course that I myself took last year when I was at Gwynedd Group as working with these guys, is Introduction to Big Data Using Apache Spark by Anthony Joseph. He's a Chancellor's Professor at UC Berkeley in Electrical Engineering. I'm going to embed in-place videos from those courses because there's no point in me explaining things that he beautifully explains and is in YouTube already. So we'll save time in the sequel, as we'll see. The next course that's really nice is Scalable Machine Learning by Amit Talwalkar. He's Assistant Professor in Computer Science at UCLA. Both these guys are heavily involved in the development pipeline of the Berkeley Data Analytics stack, so they know what they're talking about. So we sort of encourage you to take these courses already. In fact, there's a 5-module version of the course that will be starting in a month. That's a new version. Ideally, we could weave those sort of flipped classrooms in the future so that we can focus on projects. Okay, what is different about this course? This course is an expanded Scala version of those courses because we're not going to use Python, which is the main language that's used in that course. Because Spark is quadrilingual, so you can do it in 4 languages. And I'll come back to why we're using Scala. Okay, the emphasis in this course is on individualized course projects. So the idea is to get at least those who are enrolled for credit and maybe others who are interested to actually do a project and publish it in GitHub and directly appeal to the employers. Okay, so now the 2 recommended, okay, this is, I think, very important. So those are the numericists here. I strongly recommend the Stanford course in Distributed Algorithms and Optimization by Reza Zadeh. It's Institute for Computational Mathematical Engineering. This has got a beautiful set of notes. Let's see. So here we go. This thing loaded. Okay, so this is the science paper, which is quite nice. And the point is that lots and lots of, if you're flying robot or whatever, hovercraft, whatever, autonomous flying vehicles, and whatever, so a lot of problems transcend completely different domains because every scientist in the lab is inundated with the data deluge, right? The sensors are just overloading them. Okay, so this is the Distributed Algorithms and Optimization course. I should confess that I haven't gone and done all the homework yet, but the idea is that it's there for those who really need more mathematics. Okay. So these are the 2 main books we're going to be using. So you can go to UC Library. So if you right-click that and open in a tab, you'll come here, and then there's advanced analytics in Spark. So if you connect to the electronic resource, hopefully that'll take you somewhere, and then you can log in, and it'll give you a PDF for those who are paying the money. Right. So how will you be assessed? So I should warn that these books are already out of date. It's actually not the joke. It's actually out of date, right? So we actually can't completely rely on these books now. So we have to develop a lot of content directly from what's out there. How will you be assessed in the course for those who are enrolled? Assessment is essentially 50% of the final grade is basically attending each lab. So that's basically coming here. I think there's an attendance sheet that's flying around somewhere, hopefully. Yeah, but also those who are just here, please, you could add your name and sign it. I really appreciate it. So we can give you accounts and sort of keep track of how much resources we're consuming in the cloud. Okay, the second main thing is 50% of the final grade is for the projects, right? So it's basically very project focused. And the really nice thing is we have this Databricks project cluster, which is a very powerful cluster, unlike the teaching cluster, which we are currently on. The project cluster will allow us to go up to 30 gigs of RAM per node and scale up to 1,000 nodes if you really want to, okay? So that's fun. So we can do a lot. We can analyze every single earthquake that's been recorded in history if you really want. Okay. So the idea is that the last 2 weeks of the lectures, students will be doing their projects and presenting it. So the oral presentation will be graded, and then 40% of the report is what gives it the 40%, and that will basically be through GitHub and Gitbook. So basically, we're writing a book as we are going through this process, right? And I'll show you how to actually do it all through the notebook, so you don't even have to know anything about GitHub if you really don't want to. Okay, so now let's just do this. So I guess I should control click.
So Russ,
yeah.
Do you expect questions on the go?
Sure.
The first question I have got, when you say we do it now, do you mean that we actually do it now here, or you will just follow how you do that?
After I play the first 3 videos, I have to go back and make sure everybody that has showed up actually has an account. So in about 23 minutes or so, or less, I will just log in.
We will have all of the links you provided.
Yeah, exactly. This whole thing will be yours in like a minute once we sort out the sound. So this is Anthony Joseph. This is the first Spark course.
In the 1930s, Fisher proposed the design of experiments along with the statistical test ANOVA and Fisher's exact test. He's also credited with the quotation, "Correlation does not imply causation." This is ironic, given that Fisher was a lifelong pipe smoker and provided studies that showed any link between smoking and cancer. In the later 1930s, Deming proposed the idea of quality control using statistical samples. Lund, in the 50s, proposed the idea of using indexing and information retrieval methods with text and data for the purposes of business intelligence. And Tukey, in 1977, wrote the book Exploratory Data Analysis. This led to the development of the S and S+ languages, along with a language you've perhaps heard of, R. Dresner is a modern business intelligence proponent. And in 1997, Mitchell wrote a machine learning book that is still a bestseller today. In 1996, 2 Stanford PhD graduate students wrote a prototype search engine, which ultimately led to Google. And Microsoft, in 2007, released a data-driven science ebook titled The Fourth Paradigm. Norvig proposed the unreasonable effectiveness of data. The idea that multiple small models and lots of data is much more effective than building very complex models. And The Economist in 2010 published an issue titled The Data Deluge around the exponential growth in data volumes.
Okay, so you can do the same because all this content will be yours as well. So I just wanted to, instead of me sort of going through this is beautifully done, so I'm going to just quickly do this and look at
let's look at some of the sources of big data. Much of what we do occurs online, and potentially we could record every click, so every website that you click on, every ad that you view, every billing event, every fast forward or pause while you're watching a video, like for example this course video, every request that's made from a client to a server, every transaction, every network message, and every fault. Anything that occurs online potentially can be recorded. And in fact, a lot of it is recorded, but very little of it actually gets analyzed. And that's why I have a picture of an iceberg on this slide, because a phenomenal amount of data is collected, but only a tiny amount of that data is analyzed. Another source of big data is the users, user-generated content. This is a big source on the web and an even larger growing source for mobile devices. So every post that you make on Facebook, or every picture you send on Instagram, or every review that you write for Yelp or TripAdvisor, or every tweet that you send on Twitter, or video that you post on YouTube. Now, individually, this user-generated content is not very large, but taken across the millions of internet users, it's a massive amount of data. Another source of big data is health and scientific computing. So here on the left, we have a graph showing various repositories: Wikipedia, the Library of Congress, tweets per year, and the Large Hadron Collider. It generates more data in years than all of the other data sources combined. In the middle, we have genome sequencing data. Sequencing data, the cost of performing sequencing, is dropping exponentially, much faster than Moore's law. As a result, we're collecting more sequencing data than ever before. And so you see the graph in the middle shows exponential growth in the amount of sequencing data we have. Graphs are also an interesting source of big data. These graphs include things like social networks, telecommunication networks, computer networks, road networks, and collaborations or relationships. And some of these graphs can be absolutely enormous. Think about Facebook's user graph. In fact, later on in this course, we'll look at a picture of the user graph. Another source of big data is log files. These are files that are generated by servers around the internet. So here's an example of an Apache web server log that records every click. So every time your web browser makes a request to a web server, that gets recorded in a log file. And later on in this class, we're actually going to look at a log file and we're going to perform some analysis on it using Spark. Here's an example of a machine log file. And there are hundreds of millions of machines out there. Each machine is generating a log file like this of the applications that run, or any errors that occur in those applications, or in the operating system, or in the operating system processes. All of that gets recorded. But an even bigger source of data potentially is the Internet of Things. Here's an example of an Internet of Things device. And typically, an Internet of Things device has a processor, a little bit of memory, and communications capability. It also has some sensors and sometimes some actuators. So here at Berkeley, one of the research projects built the Internet of Things device you see in the upper right, which is a little sensor mode that measures humidity and temperature. And they put those into the redwood forest that we have here in California at different heights in a redwood tree. Now,
Let me make a brief pause and make this somewhat concrete for Kiwis. So the Emerging Researcher Award that was given to the College of Engineering actually went to someone in forestry who has lots of sensor data of the same kind from forests here. And then there's the mechatronics group that are still building robots to cut trees. Is this right?
Yep.
So that's a very complex problem. Okay, so up to funding, right? So this is when the multiple robots are going to navigate into forests and actually cut wood. So they're going to spatially do co-arrangements, right? So how do you actually process all that spatial information to make sure that the robots don't like fell the wood and fall on the other robot? I mean, so that's another whole problem, right? So these kinds of problems can be, the sense data can be moved to the cloud and decisions made up in the cloud, and then they can be brought back down because a robot will not be able to process all this information without a lot more computing resources.
taken individually, each sensor generates a very small amount of data. But imagine the amount of data that's generated from an entire forest full of these sensors. Here's another example of an Internet of Things device, an RFID tag. This is a California Fast Track electronic toll collection transponder. We use it here in California to pay our tolls on the highways. But it's also used to collect data that's used for traffic reporting, because it puts sensors that measure these transponders all over the highways. Now what can we do when we have big data? So let's say we have crowdsourcing with lots of users that are collaborating to provide data. We combine that with a physical terrain model and sensors which could either be road highway sensors that are embedded in the roadway, or they could be individual users' phones running mapping applications. We then assimilate together all of that data, and we can produce a picture like the one you see here at the bottom. This is a map of the city of Berkeley showing the traffic in the city. And what's interesting is, even without seeing the underlying physical model, you could see what the major arteries and traffic ways are in our city.
Okay, so I thought that would be a much better coverage of the story than me blabbering, right? So that's essentially a summary here of what was told by Anthony, so you can look at it. Now, just before we go in, we just have four or 6 more minutes of videos, and then we'll be done. We'll start logging in. This is just to set the stage of what we mean by data science.
So what is data science? Well, according to O'Reilly, data science aims to derive knowledge from big data efficiently and intelligently. Data science encompasses the set of activities, tools, and methods that enable data-driven activities in science, business, medicine, and government. Here's another definition of data science. Data science combines 3 different skills: hacking skills, math and statistics knowledge, and domain expertise skills. Now this leads to some interesting intersections. For example, between hacking skills and math and statistics knowledge, you have traditional machine learning. And this is the case where you have somebody who can apply algorithms at scale to large amounts of data and understand both the algorithms and the results that they see from those algorithms. Combining the skills of math and statistics knowledge with domain expertise, we have traditional research. This is where someone in a specific domain is able to collect some data and then perform detailed analyses on that data, understanding both the analytical process and the results that they get. The danger zone is someone who has hacking skills and domain expertise skills. In this case, we have someone who's able to collect a lot of domain-specific knowledge, apply algorithms to that at scale, but doesn't really understand either the algorithms or the results that they get from applying those algorithms. So if you remember the cautionary tale from last time about the Facebook analysis, that's a case where someone applied hacking skills to a large amount of domain-specific information and yielded a result that they didn't really understand. The combination of hacking skills, math and statistics knowledge, and domain expertise yields data science. Someone who can apply domain-specific knowledge at very large scale while understanding both the algorithms that they're applying and the results that they get from applying those algorithms.
Okay, so that's data science, right? So I don't know, sometimes financial engineering seems to be in the danger zone, you know, but it's also part of this. So this is actually a very interesting 1.5 minute clip on cloud.
Data science. Instead of going out and purchasing your own computers and then having to operate those computers and maintain them, with cloud computing, you rent computers from a cloud computing provider. This allows you to reduce overall computing costs and in particular your operating costs for computing. Cloud computing enables you to perform data science on a massive scale because you can rent huge numbers of inexpensive computers, perform a problem exploration, and then shut down those computers and stop paying for them. Now, to make this possible, cloud computing providers are building massive data centers that have hundreds of thousands or even million servers in them. Now, there are many challenges to building a data center that contains a million servers, including cooling, the building itself, and power, and how you actually organize the computers into modules. But people are performing research on exactly and engineering on how to build these things, and they are building these data centers. This is driving down the cost of cloud computing.
Okay. So this sets the stage for various topics.
So what does a data scientist do in practice? Well, first they start by digging around in data, trying to find interesting data to analyze. That's why I have a picture here of some kids panning for gold, trying to find those little nuggets in a lot of dirt and dirty water. So the next step is that they have to clean and prepare that data, and then they hypothesize a model. So they think about what they think might be some interesting properties of the data and build a model. They then evaluate and interpret the results of that model, and oftentimes you don't get what you expected, and so you have to go back and collect more data and repeat the cycle of cleaning, preparing that data, hypothesizing a new model, or maybe a hybrid of your old and new or some composite model, and then evaluate and interpret the results from that, and then repeat and repeat and repeat until finally you have a model that you think gives you interesting, statistically significant results. And then you want to run that model at massive scale. And so this is where large-scale exploitation comes into play. Now, some of the topics for data scientists include data acquisition, data preparation, analysis, data presentation, data products, and observation and experimentation. Now, what makes data science difficult? Many things. First, you have to overcome assumptions and making ad hoc explanations of data patterns. This is just human nature. When we see something, we immediately see a pattern. It's very hard for us to overcome that pattern that we saw and really understand, was that just something that sort of like an optical illusion, or was it really a significant pattern? We also have to be very careful about just, well, we think it might be this because, those kinds of ad hoc explanations aren't scientifically valid. We also have to make sure we check and we check and we check again. We need to validate our models, validate the integrity of our data pipeline, and so on. So think about the Google Flu Trends results. Initially, they had a very accurate model, but over time, the model became very inaccurate. And this is because the underlying conditions changed.
That's in one of the homework videos.
On Google News.
If you want.
They had to go back and revalidate their models and revalidate their data pipeline. And then they got great results. We also have to be very careful about overgeneralizing. That is, taking a model and trying to apply it everywhere. Another hard thing for data science is communicating our results. How do you convey the results of your model to someone who's not a domain expert, who does not understand statistical methods? Related to this, we have to make sure that we use statistical tests correctly. Again, think about the caveat example with Facebook, where the researchers did not correctly apply statistical techniques. Another challenge is moving from a prototype model into something that you can run in production and can actually handle massive amounts of data and deliver results nearly instantaneously. And finally, data pipelines can be very complex, lots of moving parts from many different projects and sources. And so when something goes wrong, who do you ask for help?
Okay, great. So that was just a very, very crash course on a whole week of videos. Okay, so I've compressed quite a lot just to give you a flavor. So what should you be able to do at the end of this course? Of course, you're going to be following these sessions and you'll be doing a little bit of homework. It's not going to be graded, but some light video watching and hacking. So you should be able to understand the principles of fault-tolerant, scalable computing using Apache Spark. Specifically, you should have a pretty good understanding of in-memory and generic directed acyclic graph extensions of MapReduce, which has been the workhorse for the last 15 years or so. You'll have a good understanding of resilient distributed data sets for fault tolerance, and you will have skills to process today's big data using state-of-the-art techniques in Apache Spark. You're going to stick to 1.6. And this is in terms of hands-on coding with real data sets, and intuitive. We won't have time for proper mathematical understanding of the ideas, but an intuitive understanding of the ideas behind the technology and the methods. And there'll be plenty of pointers to academic papers in the literature, mostly in the last 2.5 years or so. Technical blogs and video streams for you to further your theoretical understanding. And I'm hoping that the more numerically inclined researchers here will sort of join in and lead me to, or lead themselves to more interesting research in this area. Thanks, Paul. So what's really interesting to me mathematically, numerically about this area is that the algorithmic complexity is now tri-asymptotic. So the classical biasymptotics is memory and time. Now we have communication on the third axis. So it actually makes it very beautiful because the communication complexity is orders of magnitude more important than the memory and time. And you will see very shortly what I mean by that. So now what do I mean? More concretely, you'll be able to extract, transform, load, interact, explore, and analyze data at scale. Right? So please watch this video. This is just hot off the thing. Thanks for Ivan Sandukov for forwarding me from the Spark Summit East in New York City. It changed the outline for the week 2 already. So we will be playing with this in week 2 and week 3. This is actually a very beautiful video. If you can watch it later if you want to know what's coming attractions. Exploring wiki-click stream. Sorry, this is the one that that's the Spark Summit East one. And then that's just an example of exploring scalably. Now, we also want to be able to build scalable machine learning pipelines. So what do I mean by this? We want to be able to apply standard learning methods via scalably servable end-to-end industrial machine learning pipelines. Servable means it should be served to the end users with an app or whatever, or a robot that's had to make a decision on how to cut. And then it should be scalable so that if the robots are actually swarming through all of New Zealand's forests, let's say, then they should all be able to, cut the wood at the right rate or whatever. So that's basically what I mean. And we want to be able to do ETL, model, validate, test, re-ETL, which means feature re-engineer, model, validate, test, and so on, and serve the models to the clients. So this is Spark 1.6 already. This part of the machine learning pipelines is what outdates those 2 books already, right? So we will try to move you very quickly toward this. And we will choose from this list. This is going to depend on, on the interests of various people, right? So we'll do supervised learning methods. We'll definitely do regression and some form of classification, maybe some clustering or recommender systems. So it's using alternating least squares. We will possibly get into streaming and maybe graph processing or geospatial data processing. Maybe topic modeling. We have a couple psychologists here, so it'll be great to get into topic modeling, which will allow them to actually explore all of social media texts into groups and try to extract whatever these guys want to extract, right? So, we will do a word count hopefully toward the end on a PNAS paper on the State of the Union addresses of US presidents. We'll see if probably we'll spill into later. So this is a nice video you can watch to understand what I mean by creating an end-to-end machine learning data pipeline. This is actually, I think he's the current CEO, but this is a Spark Summit 2015 talk. It's a really good talk. Okay, here are extra videos for you. I've sort of handpicked them from Joseph's first couple weeks course. So, you can watch this if you like to understand what the excitement is about and blah, blah, blah. And there's other things like that are very useful, like how do you contrast this from traditional databases, right? This is called NoSQL databases because it's sort of distributed, but they're sort of more traditional databases. How do you contrast it with scientific computing, like high performance computing? And in fact, there are nice ACM articles on how high performance computing has to be in a symbiotic relationship with the scalable pipelines because they kind of 2 communities that have diverged, and a lot of innovation will come when they come together as sort of the ideas here. Okay, so here's the summaries of these videos as well. And of course, you will have all of this, so you can mark down, clone this, which we will get into in a minute, and then you can actually share this however you like. So that's basically, now why Spark, right? So this is basically, why are we interested in Spark? Spark is actually a substack of Badass, right? What is Badass? Badass is Berkeley Data Analytics Stack, right? So Berkeley has an interesting tradition of electrical engineers, computer scientists, mathematicians, and statisticians actually working together, right? So the complexity of the mathematical algorithms are actually understood in place of what's engineering and what's feasible, right? So that's a nice thing about Berkeley, and I think this municipality part of Obama's grant. So I'm going to just play Eon Strika's State of the Union address at AMP Camp 6, and we will just get a very nice overview of what Badass and the Substack Spark is all about.
And today we are here at the AMPLab 6. We have over 210 people registered. And again, thanks for being here. So AMPLab is hosted and by the AMPLab, as you well know. And AMPLab was this project started at Berkeley in 2011. It was a 6-year project, so we still have 1 year. And it was a fantastic partnership between the public and private sector. We got funded by NSF, DARPA, and Department of Energy from the public sector, the government, and on the private sector, we are very happy to have worked and still working with some of the greatest companies. Amazon, Google, IBM, and SAP have been the founding sponsors, and then we had, I think, like over other 30 sponsors during this time. I think we started the AMPLab in 2011. And one of the main goals of the AMPLab was to build this next generation of the open source analytic software to be used across academia and industry, and this is BEDAS. So what is BEDAS, going in more detail, it's about, like I mentioned, it's an analytic stack, big data processing stack, and basically it consists of 3 layers, like many other analytic stacks. It's a storage layer, it's a resource management layer, and processing layer. And the storage layer and this stack, it doesn't exist in isolation. It's actually interoperates very well with the other big data stacks in the industry, in particular with the Hadoop stack. So actually, as a storage layer, we leverage the existing storages out there, like HDFS, S3, and so forth. And on top of that, we provide some layers which gives you extra functionality, like Succinct, which you are going to hear today. It's one of the newest projects in the AMPLab, which allow you to query on compressed data. Tachyon is a project we started 2 years ago, and you are also going to hear about it. Actually, it's quite a mature project and successful project at this time. We started to provide you a memory storage layer. And then at the next layer, the resource management layer, we have Mesos, and Mesos was actually the first large project we started in the context of the Beda stack. This is where everything started from. Mesos is from everything started, and we also interoperate, like I said, with the existing stacks, and in particular this layer with Hadoop YARD, resource manager. So you can use either of them with the components, the rest of components you develop. And finally, the processing layer is where the bulk of our effort went. And here there is the bunch of systems. The most important one has been Spark, which is a parallel execution engine. You'll hear more about that. And on top of it, there are a lot of other components, libraries to provide support for different workloads from streaming, machine learning, SQL, and so forth. And finally, we also started this project 1.5 years ago, Velox, which is a serving layer, right? So you have your recommendation engine, you produce the results, so you want to serve this recommendation to the end users, okay? So today and tomorrow, you are going to hear only about a subset of these components. It's impossible in 1.5 days to go over all of them. And in particular, you are going to hear about the status and what's new in Spark. And Spark is, again, it's a substack in this stack, right? Like I mean, everything there is in blue. It's what Spark is today. It's a Spark core with the execution engine and these libraries on top of it, like I mentioned, to provide support for different work.
Okay, so in fact, there is actually a meetup group in Auckland. So there's a company called Datamine that actually has uses Spark in Auckland. So meetups, we don't have quite an official meetup in Christchurch, but there are some Christchurch Sparkers here. You know. So that's badass State of the Union. That gives you an idea. So we are focusing on the Substack, which is Spark. So here's just key points from the video. Now, the big data problem is essentially we need to appreciate why we cannot use single node computing.
Tools that we use include unit shell commands, pandas, and R. One of the things that all of these tools have in common is they all run on a single machine. The big data problem means that data is growing faster than computation speed. We have many different sources of data, and those sources of data are growing. Web, mobile, scientific. Storage is getting cheaper. This means people are saving more data. And the size of storage is doubling every 18 months. We can save even more data. But CPUs are not increasing in speed, and we have many storage bottlenecks getting data in and out of this massive storage. Some examples of big data include Facebook's daily logs. They're 60 terabytes in size. Every day, they collect 60 terabytes worth of data. The 1,000 Genomes Project has 200 terabytes of human genome data. Google's web index is estimated to be larger than 10 petabytes of data. Now, driving all of this is the fact that storage has really dropped in cost. A 1 terabyte disk is only $35, but it can take 3 hours to read the data from the disk or write it to the disk. The big data problem means that a single machine can no longer process or even hold all of the data that we want to analyze. The only solution we have is to distribute the data over large clusters. Here's an example of a large cluster, one of Google's data centers. It contains tens of thousands of machines. How do we program this thing?
Okay, so that's basically what's under the hood of the cloud instance here. So this is, so some of you may find this boring, but let's get everyone on the same physical space of what's computable.
Hardware we have for big data includes lots of hard drives and CPUs. The question is, how do we organize these CPUs and hard drives? One approach is to put them all in one big box. This is a solution that people used in the 1990s. But it was very expensive because these machines were only produced in very low volume, and they were considered premium hardware. And for today's big data, these machines are not big enough. The alternative that we use for big data today is consumer-grade hardware. It's not the gold-plated servers that we put traditionally into data centers, but rather it's more desktop-like kinds of machines. These machines are very easy to add in terms of capacity. They're much cheaper for an individual CPU and disk than traditional servers. But they're not as reliable, and they're much harder to manage. The trade-off is we'll deal with this complexity in software instead. So some of the problems that we have with cheap hardware include failures. So Google's numbers are that you lose between 1 to 5% of hard drives every year, and 0.2% of memory chips per year. Also, network speeds are much slower than the shared memory speeds that we found in those big box 1990s solutions. It's much slower to read something over the network, and the network can be much slower than reading something from a storage drive. Also, these machines have very uneven performance. Some may be very fast, others may be very slow, sometimes because they're failing.
Okay, so that's why we need some sort of fault tolerance. So how do we accomplish fault tolerance? So that's the fundamental problem that was solved using
What's hard
resilient.
about cluster computing? Well, one challenge is how do we split work across machines? Let's look at an example. How do we count the number of occurrences of each word in a document? So here we have the document, I am Sam, Sam I am, do you like green eggs and ham? We'd like to count the words. So for example, there are 3 occurrences of I, 3 occurrences of am, 3 occurrences of Sam, and 1 of do, and 1 of you, and 1 of like, and so on. So one approach we could do is to use a hash table. So here, we start with an empty hash table, and we look at each word. We start with I. I doesn't appear in the hash table, so we add it with a single occurrence. We then examine the word am. Am does not occur in the hash table, so we add it with 1 occurrence. We look at Sam. Sam occurs not at all in our hash table, so we add Sam to our hash table with 1 occurrence. Now we see I, that appears in our hash table already, and so we update the value to 2. And we can keep doing this for each of the words in our document.
Okay.
How do we deal with failures? So in this case, the first machine has failed. The simplest solution is to just launch another task, either on that machine if it's recovered, or on another machine. How do we deal with slow tasks? So in this case, all of the other tasks finish quickly, but the task that was running on machine 1 hasn't finished yet. All we do is just simply launch another task and then kill that original task. We can launch that task on a different machine because maybe that first machine was about to fail and it's running very slowly.
Okay, so here is the main idea now of MapReduce.
With distributed execution in MapReduce, each stage that we perform passes through the hard drives. So the initial step of the map reads data from the hard drive, processes it, and then writes it out to disk before we perform the shuffle operation to send data to the reducers. At the reducers, they read the data in from disk, process it, and write the results out to disk. As a result, if we have an iterative job, so here a job that has 3 stages, and we're just repeating that, so we do stage 1, stage 2, stage 3, then repeat stage 1 again, then there will be a lot of disk I/O operations for each repetition. You can see this in the figure above the stage 1, stage 2, stage 3 diagram. Each of those mappers is reading in data from disk, then writing data to disk, only to be read back again from disk by the reducers, written to disk by that reducer, then read again by the next stage's mapper, and so on. The problem here is that disk I/O is very slow. So if we run in iterative jobs, they're primarily going to run at the speed of the disks instead of the speed of our CPUs. This is a motivation for Apache Spark, because it's not just iterative jobs that we want to perform when we're doing data science, but also complex jobs like interactive mining or stream processing or interactive queries. In each one of these cases, we start with some source data, and we repeatedly read that data and perform calculations and write data back out to disk. That high amount of disk I/O means things are going to run very slowly because, again, disk I/O is very slow.
Okay, so now the idea is to use memory instead of disk.
Technology trends show that the cost of memory is dropping. Here's a graph that shows the cost of memory with, on the x-axis, the year, and on the y-axis, price. And this is a log linear plot. And so you can see that memory is dropping exponentially over time. In 2010, it only cost 1 cent per megabyte. Now, what does this mean? Cheaper memory means we can put a lot more memory in each server. So now, the hardware that we have for big data is lots of hard drives, lots of CPUs, and lots of memory. So this gives us an opportunity. We can keep more data in memory instead of writing it out to slow disks and then having to read it right back in from those slow disks. So this opportunity led to the creation of a new distributed execution engine, Apache Spark. So we'd like to use memory instead of disk. Remember that what happens when we have an iterative task is you read in data from disk, process it, write it out to disk, read it in for the next iteration, process it, write it back to disk, and so on. Similarly, when we're performing a query, we read information from disk, perform that query job to give a result, and then for the next query that comes in, we read the data back in all over again and present a result. And if we're operating interactively, this is going to be very, very slow. So instead, what we'd like to do is use memory, and use memory for in-data sharing. So here, when we read in from disk for iteration 1, when we're finished, we write it to memory. And that way, iteration 2 can read from very fast memory and write to very fast memory. The same thing with our query. We do a one-time processing step to read our data into distributed memory, and from there, all the queries run from memory. This can be anywhere from 10 to 100 times faster than using the network or the disk. The abstraction that Apache Spark provides is that of the resilient distributed datasets, or RDDs. We write our programs in terms of operations on distributed datasets, and these are partitioned collections of objects that are spread across a cluster stored either in memory or on disk. We can manipulate and build RDDs using a diverse set of parallel transformations, including map, filter, and join, and actions, including count, collect, and save. And Spark automatically keeps track of how we created the RDDs and will automatically rebuild them if a machine fails or a job is running slowly.
So that's the major trick, is to keep the recipe for creating the objects you were after. That's called the lineage graph, basically. And that sort of brings, it's the last video, brings
Let's talk
us...
about the differences between Spark and MapReduce. In MapReduce, your only option for storage is the disk. In Spark, it supports both in-memory storage and on-disk storage. In terms of operations, MapReduce only supports the map and reduce operations, whereas Spark supports map, reduce, join, sample, and many other operations.
Okay, so in the interest of saving time, you can look at it because some people will argue about the differences. The points that are in this video is basically quickly summarized here in the interest of time. Spark demonstrated an unprecedented sort of 1 petabyte worth of data in 234 minutes, running on 190 Amazon EC2 instances in 2015. Right? So it's pretty fast. So here are the key papers. So these are historical milestones. So history starts in 2002 for a lot of this stuff. Of course, it's building on top of list processing and scheme, and there's really only one language in some sense, right, in computer science. So anyway, this is a big, and the details are here. This is essentially 1956 to 79. Stanford, MIT, CMU, and other universities develop a set of list operations in Lisp, Prolog, and other languages for parallel processing. And then fast forward to 2004. This read I'm saying because I've read it, and I strongly recommend it to be a reading if you don't want to read everything. This is Google's MapReduce, simplified data processing on large clusters, because often that's the storage layer, right? But what we are doing in Databricks Cloud is S3, which is Amazon's proprietary version of some form of this, right? The engineers can like shut me out when I'm blabbering, you know. So that's, and then these are Yahoo's Apache Hadoop and cloud computing. These are extra reading for the engineers who want to know the history of ideas. And then this, I think, is the main paper. This is for Hadoop. Then we fast forward to the Spark core paper. So this is basically cluster computing with, this is what RDDs are introduced. Essentially, you keep the recipe to build the objects so that if one machine crashes, you can go back from the recipe and recreate that bit. It's kind of the high-level idea. We will encounter this more in the sequel. So I strongly recommend you read this one. This is the more detailed paper. It's sort of the timeline. All right, this was supposed to take 20 minutes, so I think we are. So this is marked down, right? So I'm just basically writing notes. How many minutes have elapsed? 25 plus 30 is 55, is it? Wow, okay. So anyway, stuff will spill over to week 2. I do less notes, so. All right. Okay, so 55 out of 90 plus 10. I don't know if you want to do it the Swedish way with no break and have a lot of meat in the end, but I can't provide meat, so we'll maybe take a break depending on how people feel. But the main thing I want to do next is to make sure you guys log in. That's the most important step, right? So here's some extra stuff for some historical insights. So now let's just get you logged in. Okay, so log into Databricks. So I have to beg or borrow, whatever, plead that please follow, especially the faculty that are here and other students who are non-fee paying people, please follow these 21 easy steps for sharing your AWS Educate credits. Without this, we cannot run this course, right? Because it may seem a lot, but that's what you're giving back. Because everyone, I said, has AWS credits, so you have to share those credits so that your AWS credits will be fueling the AWS cluster under the Databricks hood, right? So Paul has made these steps, exactly what you need to do. If you have a UC email address, it'll automatically work for a UC Live account or .Canterbury account. Of course, if you don't have a UC email address, then you cannot contribute AWS credits because you're not in the, okay, so it's all, and then in the end, you basically will get to the point where there's a credit code, and you just need to forward it in an email to me, okay?
Why do we need to do this?
Because I need AWS credits to actually pay for the AWS cluster that's running under the Databricks cloud.
Can we use our external AWS account?
No, it's not, because this is academic, so this is not for, yeah. So I think you just, because you definitely are paying enrolled students, so you have the UC email. So if you just follow those instructions, then.
So it's because AWS doesn't talk to Databricks, so we need to connect them.
That's right. That's exactly right. Okay, so that's that would be helpful. If that's done, then we can really do really fun projects, and I'll tell you more about the projects in a minute. So here are the 7 steps to get into the Databricks cloud. Let's go and do that first. So first you have to go to www.map.canterbury.ac.nz/Databricks. So please type this URL on your say Firefox browser. Okay. So how many of you have already logged in? Please raise your hands. Okay.
Databricks.
Yeah. So if you go here. You know what I mean? So if you go to, okay, so if you go here.
Yeah, and yeah, what's the password?
Okay, that's what. So once everyone is here, then the password is written here. So your email address is the email address that was on the form that was sent around. Password is capital O. Only map unknown is unused. Okay, but E is 3, I is exclamation. Okay, U is capital. So only map unknown exclamation is unused 3D. Okay, that's my favorite quote from Lucien Lecam.
Jim needs to make for Windows.
So who can't log into a machine? So this is on.
Paul put me into Windows with some guest account. So I'm actually on, and I don't remember the Windows.
That's fine. She's got her own. Yeah. I have guest accounts that you can log in. So all these
Only master knowledge.
Okay, so all right, so then okay, yeah, well, yeah. Okay, so how's
Should we change that password as a default for us?
yes, so the next step, may I move to the next step? So the next step is just to change the password immediately. Right, so you basically will be taking, is everyone here? Is everyone in this prompt? Okay, great. So then change your password immediately. So you go to this person icon and click account settings.
Oh no.
Okay, let me check. Okay, so please raise your hand if you're behind or something. Okay, so then you basically change your password, and then we'll. Who else has problems logging in? That's yeah, well. Has anyone successfully changed password? Okay, all of you are good. You guys are good? Yeah. Okay, so all of this side is good. Okay, so basically. So those who pre-enroll but didn't enroll or essentially were not in the system. So, okay, now let's move to the next step, which is now recognizing your home area in the workspace. Okay. So basically, you have to go here. If you go to Home icon, it'll immediately show you where you are. So I'm enrolled as a student, tab 137 in the screenshot. So this is essentially your area where you can read and write. Okay. You can read everything else, but you can only read and write here. by default.
Here, where?
Here meaning, so if you go to the users, if you click the home, it'll immediately open up this and show you this. This is highlighted, and see this one's highlighted down here, pad 137, because this user is pad 137, and this is, it's empty, there's nothing here. So you should see something similar for your account. And the next step is cloning the Scalable Data Science Week 1 folder. So try to. Okay, so we basically have to go to the Scalable Data Science folder, week 1, and then go to clone, hit this clone button. So, looks like some of you are stuck with the same password thing. You can copy this. There we go. You're good. So, okay, so let's see. You've got. Perfect. Okay, so let me find that. Some weird. Managed to do some magic.
I don't know why I always ask for
And this didn't work. Then it's already here. So I'm not sure why that thing is not moving. Okay, so when you please try to you can rename the folder later. So I just call it week 1 because it'll put parentheses and put a number next to it. Okay, so then you just hit this clone button, and then you're going to be here basically, right? You'll start seeing all of the material for week 1, and then what we want to do next is go to 003 Scala Crash Course. That's the notebook we want to be on. Okay, so I basically was doing lectures based on the first 3 notebooks here, and it should look like this. Is everyone here? Okay, please raise your hand if you're not here. Okay, so Ian and...
I think I cloned the first page.
Yeah.
yeah.
Okay, you're good. Yeah, go to those things.
But I need to be in my work.
Yeah, you have to hit the clone button.
Yeah, I've done that.
Oh, you already done that? Good. And who else? Yeah. All right, so I think we're all there. So now the last step is to attaching your notebook to a cluster, right? So there is this notebook 003 Scala crash course has to be attached to a cluster. So all you have to do is basically go to this icon that says detached, click that little arrow there, and then a bunch of things will appear. So if I go here, a bunch of things are appearing because these are the clusters that are currently live right now. So this is in the AWS instances, right? So now please don't just click anything at random because of money. So those who are enrolled in the course and paying money, please do students enrolled, okay? And those who are the others, just hit the student observing one cluster, okay?
Will we be able to create a cluster?
Yep.
One more?
That's so once you've done that, you're going to say it's attached to whichever cluster you choose, and then it'll be done, and then we can start actually doing stuff. Okay? No? It's okay, so what you can do is okay, now is everyone attached to either the enrolled or the observing clusters? Okay, raise your hand if you aren't. Good. Now we are almost ready for some beautiful magic, okay? So let me tell you very briefly the essentials of Databricks Cloud, right? There are lots of words to digest. So Databricks Cloud we're going to call DBC. So these are DBC essentials. What is Databricks Cloud? Basically we have the workspace, that's what you saw, your folder structure, where you can write to in your own area and you can read everything else. Of course, you can set permissions and prevent others from seeing what you're writing to, okay? And then Spark is basically in the middle layer here. That's underneath the Databricks workspace. And below that is the Databricks platform, right? So the more physical stuff. And here are some words, DBC essentials. There's something called a shard, something called a cluster, notebook, and a dashboard. A shard is just an instance of Databricks workspace. That's exactly what you're currently looking at. This is a shard that we're going to use for lectures. The signedine-canterbury-edu.cloud.databricks.com is a shard that was approved for lectures of this course. Okay. There's another one, signedine-canterbury-research-edu, which is what we will use for research projects. Okay. This shard is limited. It only has 6 gigs of RAM per node and doesn't scale up to lots of nodes. The other shard is approved to have 30 gigs per node and scale up to thousands of nodes, right? So, of course, you know, with the Databricks, with the AWS credits trickling in, we can actually do anything meaningful with that other shard in terms of paying for the computing costs under the hood. Notebook is basically what you're looking at. A cluster is basically multiple clusters can be launched per shard, and that's exactly what you're looking at. There are 3 clusters here attached that can be attached to from this shard. Okay, that's basically the idea. And dashboard is actually evolving fast, so we won't use dashboards too much here, right? So we'll get outdated with Spark 2.0 already. So this is the idea we of a team, state, collaboration, and elastic resources, right? So here are people in the class. They are logging in through their browser into the shard, okay? And then they can basically work with local copies of files from their system if they want. And then this is the notebook. Notebook has a state, and it can be attached or detached to Spark clusters, which are being created from the cloud. So you have shard, state, notebook. people logging in. You, as a user, can allow whether other users that are connecting to this shard can collaborate with you in real time. So that's kind of how Siva and I are writing notes late at night, okay? So we can Google chat and quickly just see what they're doing, and we will explore that. In fact, if people are interested in doing team projects, whether they're enrolled for the course or not, that's a very, very effective way to collaborate. Okay, so enough of that. Now let's do some actual fun stuff. This is where everyone should be. So I think it's only Matt and I that are attached to the class cluster, and everyone else should be in the other two clusters. Okay. All right, so notebook. This is essentially notebook. It can be written in Python, Scala, or SQL, right? This is a Scala notebook because this parenthesis says here it's a Scala notebook. We are going to use Scala primarily in this course. We will dabble into R and Python as needed, okay, and SQL, but mostly we will be on working with Scala. It's because Spark itself is written in Scala, and we will not have access to the latest and greatest things without Scala. So this is how you create a notebook. You simply can go to your whatever workspace, your home. You can just basically go to any folder you like. So let me see. I think I am, who am I? I'm r.signedin here, so I can go and, whatever. Here's my sandbox. This is basically where all the material for the following weeks are, and I can just go here and create notebook, okay? So you can create a notebook, you can call it test, whatever, and it sort of pops up Python by default. Sometimes, so just choose Scala, and then it's already connected to this class cluster, right? I can choose, I can go and connect to a different cluster if I want as well. But, okay, so, and then you can start doing stuff. So %md is markdown, right? So I can say hash hi title, whatever. Control enter will, so I won't go through too much details here. That's exactly what this notebook will do for you. So let's go back here and go back to where I was, which is where you should be with your own copy now. And it's here, okay? So the stop stuff is basic. So if you go and double click on it, you will actually see what I did to mark it down, okay? So, and it's just syntax for just showing the notes. So notebooks can be written in any of these languages. You can create a notebook. You already know how to clone a notebook. So so the week 2's material can be cloned next week. Okay, you can clone directories as well. So here's an introduction to Scala through Scala Notebook. We already did this cloning. And another basic object we want is cells, the notion of a cell. Cell is nothing but a unit that makes up a notebook. The stuff that's highlighted in blue is the cell I'm currently looking at. So I can always double click it and see that it's just marked down with, hyperlinks and so on. So I would like you to start looking at things and kind of figuring out the markdown syntax. There's a lot of help for markdown because for the project, you'll be doing it in markdown. Anything you want to communicate by text, you'll be doing in markdown. Okay, so cells are units that make up a notebook. You create and edit a new markdown cell in this notebook by just going to this plus button. So I can just go here and open a new cell above, and I can go here and open a new cell below, right? So I can just click this and confirm that I want to delete it, or I can just, shift enter and delete it without a warning. So all these things are written down here, but now let's just do a little homework. Click out the cell below and do %md hello world, right? So that's here. This is the cell, %md hello world, hello world, hello again, right? Now, when I'm done typing this, I have to evaluate this cell, right? So there's many ways to do it. If you want to just remain in the cell after evaluation, then you press Control Enter, okay? So I've now just done some markdown, right? So Control Enter to basically remain in the same cell after evaluation. and Shift-Enter to just go to the next. Okay. So that's what's all explained here in detail. Okay, so there are some tips. So to edit, you can just double-click and so on. Is everyone happy with PersonMD Hello World example and evaluating a cell? Sorry, Steve. So Steve took the course with me and Jasper as well, so we sort of brain freeze, right? So it's important to be able to do those little things, right? Now let's run a Scala cell, right? So because this is a Scala notebook, we don't need to do any special %Scala, right? Its default is Scala. Later on in the bottom, you will see if you open an R notebook, which you can, then you don't have to say %R. The default language will be R for you. But you can babble into Scala and come back, okay? But how you communicate the objects between languages is a topic for after week 3. But, okay, so here's actually a Scala line. So let's go in here, print ln, this print line, system.current time milliseconds is just going to print your, so I did Shift-Enter instead of Control-Enter, so it took me to the next cell. So that's basically my current time. Here are lots of Scala resources, right? If you're serious and really want to learn Scala, you shouldn't be taking this course to learn Scala. I am afraid I won't be able to teach you Scala. I myself am in the middle of a Coursera course trying to finish Scala, but you will learn how to use Scala code to do various tasks here. So it'll be very, very task focused. So we will do like linear regression and cross-validation through pipelines and things like that in Scala syntax, right? So most of the time, you'll be slightly modifying some input file or slight changes, so you don't have to worry too much about the Scala syntax, except sort of figuring it out from what's there. I strongly encourage you to do this course. It's quite nice. And the book I really like is, there's actually many books. Martin Odersky is, I think, the Scala's founder, right? So his Scala by example is free. You can download it, and I usually look at it a lot because I have a hard copy and keep forgetting the for loop syntax in every language. So I highly recommend it. It'll get you really quickly into things. Now, Scala Crash Course by Holden Crowell is another nice quick resource. This is full on. This is free online reading, programming in Scala. Probably something more serious guys who really want to get their hands dirty would do. And please take a tour of Scala. So Darren Wilkinson is actually a stats researcher, and his blog will give you a brief introduction to Scala and Breeze for statistical computing, right? So this is for someone like Dominique or Carl. I don't know if you guys know Darren. Do you know Darren, the English statistician? So anyway, so I'm going to link in blogs a lot and embed in place. I'll show you what I mean by embed in place. So this is a brief introduction to Scala and Breeze for statistical computing. And we have some research assistant resources. So we may be able to put this thing in Markdown for us once I get permission from him to do this. But you can just go here and copy paste, so it's not, so it gives you a very, very simple introduction to Scala and takes you right into linear algebra very, very quickly. Okay, and it's Fortran and C under the hood anyway. So, okay, so what is Scala? Scala basically is a high-level language for the Java virtual machine, which is nice because it's now sort of operating system independent. It's object-oriented and functional at the same time, so it sort of combines two big camps in computer science maybe that are sort of different. It's statically typed, which gives it a huge robustness. So for example, it is an ideal language for taking the constructive mathematicians and the mathematical logicians here that are working on various problems and in fact bring that full-blown thing into here, because you can do type theory on it. Right? So that's very elegant. So it's a competitor for Haskell for that. It's comparable in speed to Java. The type inference saves us from having to write explicit types most of the time. It just interoperates with Java. So all the Java libraries that have been written over the last couple decades almost are directly accessible in Scala, right? So we can inherit from Java classes. Now, why Scala? It was because, I mean, for me, I'm not a philosopher about languages, right? I'm sure this will be something new in a few years, and I have a lot more gray hair. But Spark was originally written in Scala, right, which allows concise function syntax and interactive use. And the Spark APIs for other languages include Java, Python, R. But unfortunately, these are like sort of application programmer interfaces into the other languages, so you're not really swimming in proper Scala code in Spark. So all the DevOps things and all the contributions you can really do should be really done in Scala. Is that right? So that's the reason, right? So if you're a company and you're trying to survive to beat other companies in the world, then you want the next hottest thing to be able to sell, right? So you want to be able to get as close to the open source libraries as possible. So this is Darren Wilkinson's, the statistician again, his 11 reasons for Scala. So I met him in Scalable Bayesian Computation in Banff a couple years ago that Christian Robert arranged. So he's kind of a well-known statistician. So this is his reason for why Scala should be considered as a platform for statistical computing and data science. So now this is what I mean by in-place embedding. So what I've done is I've hidden some code here. So just to demystify this, I can say show code. It'll show me %run, and then I have a particular place where I have a function called SDS functions, SDS Scalable Data Science function. So there, in that worksheet, which you can find, I've defined a function called frameIt. Okay, so I'm just going to hide it, and so this is how you can call code from other notebooks into other notebooks very quickly. We will play with these ideas later. So frameIt basically takes a URL as input, and then how much horizontal space you want, and embeds it in place using the display HTML function in Spark, right? So in Databricks. So that's what I've done. So I've basically embedded Darren's blog right here, and I'll be doing a lot of this so that you don't have to move around too much. So you can just start reading Darren's blog here and then come back, and it'll be left where it is. In fact, you can even navigate here. You can go, let's go here. So you can navigate within the browser itself. But if you do that, then you have to basically do right-click and then go back. Okay, so this is sort of intra-embedded navigation, right? So you cannot use this back button. Right? So that's the only thing, right? So if you want to navigate within here, you just right-click and then use the left arrow and right arrow. And now all of that is explained, I believe, in the worksheet. So here's a feature wish list, and you can read about why he thinks Scala is good for statistical computing if you're interested. So let's get our hands dirty in Scala, right? There's a lot of talk. So we'll go very quickly through assignments, methods and tab completion, functions in Scala, collections in Scala, and then the notion of Scala closures for functional programming and MapReduce, right? So this is basically the heart of it, these notions of closures and functional programming, which is how we're going to talk to different processes in our machine learning pipeline down the road. Okay, how do you assign? Val is actually a value. It's a constant. It's immutable. So you would say val x, value x of type int equals 5. So this would be if I control enter, I'm evaluating it, and it tells me x is an integer. That is 5, right? Now Scala is statically typed. So because I can just go here and do control enter again, and then what I'll find out is x is just 5, right? And I didn't have to say colon int, because Scala has a very nice type inference machinery, and it knows that because I didn't put a 5.0, it knows it's not a decimal, so it'll actually figure it out and do the type inference. So it's statically typed, but it's inferred. Types are inferred. Okay, now this is just some examples. Let's declare x as a double or double precision. So all I have to do is val x equals 5.0, right? Now, don't put 5 point like you do in MATLAB, because it's pretty precise. It's actually 5.0, right? It'll complain because they changed the standard there for the dots. Okay, so now we have double, right? So alternatively, we can assign it like this as well. This is like a much more paranoid way, and maybe definitely a good way a programmer will implement it to make sure there's no clashes. So here's again x equals 10. So now I'm trying to reassign 10 to the value x that I created earlier, and of course it complains because this is immutable, right? It cannot be reassigned. X, which is a value, is immutable, so it cannot be reassigned. Okay, which is good. That's what makes it very safe. One of the things it makes. Now I can, well, then I can do var for variable instead of val for value, and then I can simply go y equals 2, var y equals 2, so that's int 2. Now I can, of course, change y to be 3 because it was declared to be a variable, so it allows reassignments. Okay, so methods and tab completion. So let's create a string val s, value s equals high. Again, it did type inference from the quotes that it's a string. So it says it's string equals high. And then what I'm asking you to do is place the cursor after the dot and then see what happens. So we go here, s dot, and then I hit the tab button. Now I'm actually seeing all the methods that s can be applied to. S is a string, so these are the methods that, so you can ask, is it empty or whatever, what is its length and so on, right? So there's a lot. Okay, so here are some examples here. You can ask if s contains an empty string, s contains the value I, and so on. So let's just shift enter here, as it says, and then ask if s contains f. Oh, I made a boo-boo here. Sorry. Oops. Okay, s contains f, and Boolean is false. It returns a Boolean because it's a predicate, and then s contains the empty set. Well, also empty string. So sure, every string contains an empty string by definition, so it's true. Does s contain I? Yes, it's true because the string s was high. Yeah. So sorry, man, I have to start with strings, functions, val, var, everything. So that's course from computer science, actually. So I'm taking this machine learning course as well. So def square x colon int. Okay, this is how you define a function. Unfortunately, it's very, very important to be a little bit precise about the types for functions. So I'm saying the input argument x is an int, and the output argument is an int, and the operation is x times x, right? So let me shift enter. So now I've defined the function. It's very similar to Python, but and then I can square 5, right? I can call the function on 5, and I can basically recall that what value y is, square y, and so on, right? So I'm going to move here, right? So I can do the same function a little bit more cleanly with a block, right? So I open the code block with the parent brace, left brace, and right brace, and in the middle I do val answer equals the value, right? Answer equals x times x, and then I'm returning the answer, basically. And then I can do, so let me do that. And then I can do square of 5,000, shift enter. So that's nice. And then this function is basically announce and emit. So it's basically saying print the text that was passed in. So it's just another example with just text. So please go through this. Because I'm just saying Roger, Roger, right? So so anyway, Roger is the CTO of Vineyard Group, and it's because of him this course is running. So I should be very grateful for Roger. So anyway, so Scala collections is the next thing we need. We need list. So val list, again, value list is the list 1, 2, 3. So we can just control enter there, and then we've created a list of integers of list 1, 2, 3, and then R. Okay, we're just going to create an array. So I'm going to shift enter, and that creates an array int, which are slightly different objects. They're both sequential containers. And then seq is also another sequential container. So, we'll play with them. Seq basically goes into list. Okay, so that's enough for Scala collections. So we can have collections, vals and vars. Collections themselves can be values, immutable, or variables that are mutable. Okay, so now the last concept is Scala closures for functional programming and MapReduce, right? So here are 5 ways of adding 1. Right? So the explicit version is you just say x is an integer, and then you put this equal sign and right arrow and say x plus 1. This is a type inferred, more intuitive version. X maps to x plus 1. And this is a placeholder syntax. Here this is underscore plus 1. And this is a type-inferred, more intuitive version with code block for larger function bodies. So a good software engineer will write more like this, okay? So of course, Scala gives you a lot of ways to code, which some people really hate Scala for it. I will try to stick to very simple syntax, because I only know a couple myself. So and it's enough to do it this way, because it'll be quite mechanical to understand what the closures are doing. So let's see some closures in action. Here's LST, so I'm doing a method called for each. So remember, LST was a list, so I do for each. And for each, what I'm doing is this closure, which is take X, each element of the list, and do a print line. So it's just printing it in line by line, 1, 2, 3. This LST had 1, 2, 3. I can also do LST for each. I'm not sure. So in this case, I'm not putting print ln of X, because it sort of tries to figure out what you're trying to say a little bit, right? lst.map x equals x plus 10. So now I'm taking each value in the list and adding 10 to it, okay? So that's basically 1 plus 10 is 11, and 2 plus 10 is 12, and 3 plus 10 is 13. So now lst.map, okay, so I'm mapping each value. I can also do the same operation with this underscore notation. I'll try to avoid underscore notation as much as possible, right? Because it's very convenient, and then later on it'll bite you in the back, because it's hard to, you can just do some very complex Scala code that only you will understand very quickly. So we'll do things more mechanically without the underscore notation. So here's basically a filter operation. So I can take the list and filter elements from the list if x mod 2 is 1, right? So basically, I should now get only lit 1 and 3, because 2 mod 2 is 1. So it's just filtered it out. And then here's just the underscore notation for the same operation. And then this is the other really important concept of reduce. We talked about map and reduce in all those videos. So what is reduce doing? Reduce is going to take 2 elements at a time and do a reduction operation, right? Usually this operation should be associative and commutative if the order of the pairwise operations shouldn't matter, right? So addition is one of those reduce operations that will preserve associativity. Okay, so now I can just do, so I've just added every element in the list. Now, what is the difference between reduce and just doing a for loop, you should ask, right? Why can't I just go a for loop? Well, because with reduce, I'm doing a pair at a time, so I can have a huge list of billions of numbers spread through the entire cluster, and I can add them 2 at a time and have them all trickle up, okay, through the network, the Ethernet cables and so on. So that's what's powerful about reduce. Okay, this is just, again, underscore notation for reduce. Okay, so now let's combine map and reduce program to do this, right? Because of the dot operator, we can say list.map x goes to x plus 10. So we add 10 to every element of the list, 1, 2, 3, right? So let's be really paranoid, because I am quite paranoid. So we know that's 11, 12, 13, right? So now let me uncomment that bit. Now I'm just going to do the reduce. So that should be 11 plus 12 plus 13, which is 36, right? So that's essentially all we minimally need from Scala to continue, right? So Spark was written in Scala, as I said, so that's essentially our main language for this course. However, let's use the best language for the job, because there's no point. I don't know if anyone watched the Spark Summit New York, sorry, not Spark Summit. There was a video about scikit-learn and Spark this morning, streaming from California, 7 to 8. There they're using scikit-learn, and it was really nice for drinking coffee and watching it. Why do you want to reinvent all this amazing data science tools in Python already built? So you can just use it and you can interoperate it with Spark. So we will definitely use multiple languages, and it's trivial to use multiple languages. All you have to do is, well, we already saw %MD for Markdown. %SQL is for SQL, so which we will do later toward the end of next week, I believe. And then %Scala is just, you need to do this if you're in one of the other languages, right? If you're in a notebook in Python, then you have to do %Scala to call Scala. You can do %Py for calling Python from within here, and %R for R, right? R is slowly coming there. It doesn't have all the functionality. Maybe next year, pretty much everything will be in R, so we can just do it. Not this course, but other courses in the department can be done in a fully scalable way using pure R syntax. Okay, so here's, for example, %Py print, right? This is just Python, and this is %R print, right? So this is a trick because it's exactly the same syntax for both languages, but trust me, you see the output, right? They're different. All right. Now, here the command line cells can be used to work with local files on the Spark driver, right? So this is how I showed you the %sh is the shell, right? So I can actually do %sh, do these comments, hash comments, and I'm currently in bash, right? So I'm calling man bash, I'm reading the man pages of bash, which is basically, right? And then I can actually go read the man page, which means all of shell, bash shell, is under your fingertips. And in fact, this is how we pre-processed. Paul did most of it, the State of the Union addresses from this, did some web scraping for this word count thing. Okay, so I think maybe this will stop after this worksheet. So the file system cells allow us to access Databricks file systems. So this is %fs for file systems. And we need to really be able to use %fs to start accessing local files and also files that we want to load into a distributed file store. So here's further reading and homework. Please, enjoy your evenings or nights, whatever you do, reading stuff like this. So they're all nicely hyperlinked. These are very nice notebooks to be aware of. Right. And there's introduction to Python and R, so people that are more into these languages can just sort of right-click and continue some of the stuff there. Okay, so I can now do run Databricks guide 00 welcome. Right, so this is one of the recommended things, and I can just run that notebook, which is actually in Databricks guide. By the way, I should point out that Databricks guide is just here. It has a lot of stuff. In fact, what I'm doing is sort of elaborating some of the modules there in this course. So it's just pure syntax if you dive into this. So that's essentially, I think, introduction. Okay, so some of you may know Scala, others may not. So then what happened is I basically called the other notebook here. And it basically tells you a lot of things you already know about creating clusters and so on. But it has some very nice videos in the bottom. So you can just watch these videos if you're too tired to read. So these are just overview videos, notebooks, and stuff like this, right? How to access and when am I supposed to finish?
Where is this video?
You want to watch the video? So let's.
You said that there were some videos.
Yeah, so we basically go to Welcome to Databricks and Databricks Guide. You can go directly and then you can clone it, for example, put it in your wherever, and then the videos are on the bottom. So you can do it that way. That's probably the sensible way. Then at least when you clone it, you know which parts of the Databricks Guide you have yourself gone through, which helps a lot. And they change things as well with the new version. So, okay, so that's essentially, I'm afraid, 1/3 of what was originally planned. Well, okay, look, guys, I'm figuring out the timings and stuff, right? Because it's a very mixed audience. So I normally wouldn't have to do a Scala print ln to a different audience. But let's just see how it goes, right? So that's essentially the end of that worksheet. The Spark Essentials basically was about RDD transformations. And yeah, so, I mean, how are you guys feeling? Do you want a break or you want to go home? Okay, so yeah, so those who are not enrolled, can do whatever they want, and then, yeah. So let me quickly tell you what's coming at Traction. Maybe we'll call it a day and continue next week, shall we? Okay, it's a lot to take in, right? So briefly, the coming attraction is I'm going to next start into RDD transformations and actions. These are the core ideas in RDD, right? So this worksheet basically goes through what's a program, driver program, cluster manager, worker node. You already have the nodes, so please feel free to dive early, and then whatever. So this is an embedded one. There are videos, I was going to play them here because they're quite short. It's only 48 seconds, 1 minute. And then there's a summary already, so you're welcome to go through all of this yourself. And then we can maybe continue from there. So it talks about basic actions called collects, takes, maps, how do you do maps on RDDs, and then filters, and then flat map, and then key, reduce by key. So with just those operations, what you should be able to next do is do the word count. So there's a homework one here. So this is for next week or whatever this week. You feel free to knock yourself out. There's a lot more exercises here to learn. And then word count is what is the hello world of this space, right? So word count on the US State of the Union addresses. So this is actually a nice PNAS paper. I think the psychologists and the humanists here, or maybe listening in from New York City, if you're still there, may want to read this paper, and it's a very beautiful paper. It's a recent PNAS paper, and they analyze the State of the Union addresses of all US presidents, and it's kind of very interesting what they're doing. But we will start from first principles. So this has already been mined for you, scraped for you. It's just in a different worksheet, and this Paul did most of this. And what has been done here is basically a huge bash shell command that produces the raw text from the web pages. So a data scientist has to do this. It's not somebody else's toilet. You have to clean your own toilet or generate your own data. So then once that's done, then we basically will load it into the distributed file system and start looking at what George Washington said, fellow citizens of the Senate and House of Representatives in 1790. And it ends with Obama. And we'll do a word count quickly with all these ideas. Basically, collect, flat map, sorry, it's just map, reduce, and reduce by key, and flat map, and then some filter. And then what we will be able to do is essentially find a nice ordering of words. So you can actually have a word count, State of the Union 1790, January 8th of Washington, sort by, you'll understand what all this stuff means. So I think he said the word "the" 97 times. That's the most said word by George Washington. And you can kind of look at how sparsely spread out it is. It's very different. And then you can look at Obama's speech in the last 2016. And then he says "the" 264 times, like the, you know what I mean? I don't know. So yeah, it's very different, right? And in fact, but what this PNAS paper does is much more beautiful. They actually look at co-occurring words and things that Steve Mannion knows more about, so context determination. And so we're not going to do that in that worksheet, but this is a very nice project proposal. Somebody interested in text analytics and social psychology or digital humanities or whatever can kind of start using this in a fully scalable way. Okay, thank you very much. And please hang around if you need any help or have questions.